All right, I'm thinking about putting a team together. You guys got anybody in mind?
Well, I think Bootstraps would be a great candidate.
Bootstrap makes sense, but we need something to, complement.
P-value!
Oh my gosh.
You see what I'm saying?
I see it.
Yes!
Let's put this hypothesis to the test.
With confidence, that's significant.
Welcome to a significant lecture, Bio 6618 on Bootstrap p-values. We'll first briefly refresh ourselves of what the Bootstrap is and what we've discussed in class before. We'll then discuss a few different approaches and walk through an example in R of applying the Bootstrap p-values. So let's start with the review. We've previously talked about a two-sample Bootstrap and case resampling. Now, the idea is outlined in the slide here, but essentially Bootstrap sampling in this non-parametric approach mimics how the data were obtained. So for an example designed to compare two populations, we might randomly take a sample from each. Therefore, the Bootstrap will mimic this process. So given these two samples or groups, we'll take independent sample sizes of m and n from those populations of interest. We'll then resample within the first one with replacement of size m, and likewise within the second of size n, also with replacement from that sample, and compute our statistic of interest that compares the two groups. It could be the difference of sample means, a ratio of variance, or any other quantity we might come up with. Now, because this is a resampling process, we'll do this many times, let's say 10,000. And then we'll construct the Bootstrap distribution of our statistic, inspect its spread, bias, and shape, and summarize our results. This was the basic formula or foundation we used previously in the semester. Now, in the past, when we've discussed what these bootstraps can do, we've discussed how they can be used to estimate the standard error for our estimators and statistics, and to construct confidence intervals. And the two specifically we covered were that bootstrap percentile and normal percentile intervals for these unknown parameters. And the really nifty thing about Bootstrap is that we really don't need to know in this non-parametric approach anything about our statistic of interest to be able to estimate these quantities. Well, one question that keeps coming up is, well, can we somehow estimate the idea of a p-value or p-value-like summary for our bootstraps as well? Especially considering we can construct confidence intervals and interpret them for significance. And that's the point of this lecture, to show how we can calculate p-values for test statistics under a null hypothesis, and we'll see that this is very important, which is a new assumption we didn't make for points 1 and 2 above for standard errors or confidence intervals. So let's touch on this a little bit more. Why are we focusing on the importance of resampling under the null hypothesis specifically? Well, let's go back to also our lectures on the definition of a p-value and this null hypothesis significance testing framework we have for most frequent test statistics. In order to estimate a p-value, or the probability of observing something as or more extreme than what we observe assuming the null hypothesis is true, we need to resample under a null distribution. Now, producing a null distribution with bootstrap testing can be somewhat nuanced, and it depends on the test statistic of interest. And we're going to discuss this in greater detail for comparing two group means in the next section to motivate some of these approaches. Now, before we get there, though, you might have a slight case of deja vu. With regards to this idea of resampling and null distributions, you actually may be thinking about the permutation test, which is another resampling strategy. In our previous lectures, we noted that this approach resamples without replacement from a pooled dataset. In other words, we combine all xm and yn cases, and randomly assigns labels for belonging to either group X or Y with m or n spots. This process for permutation testing always generates the null distribution. However, permutation tests are limited to contexts where groups under H0 have the same distribution or are otherwise thought to be exchangeable. And this may be true in cases especially like randomized trials, but it can require stronger assumptions about your study design or setup in other settings. And we'll also note that we previously noted you can't just combine the resampling bootstrap with replacement with the permutation test without replacement due to the different assumptions we're making about these underlying distributions. So with that refresher and motivation behind us, let's look at some ways we might be able to approach calculating bootstrap p-values. Now, to help provide a more concrete setting, let's look at a motivating context for this p-value calculation for bootstraps. And let's assume we are looking at test statistics that is the difference in group means, such that we have something like a statistic t here that we're defining to be mu x minus mu y in the population. Now, suppose we take a sample and we actually go out and we estimate right over here this quantity t naught, or x bar minus y bar. This will be the value of our test statistic t from that particular sample. Now, the idea here is that we're then going to proceed to calculate T1 to TB star bootstraps, resampling from a null distribution. Again, highlighting that importance of that null distribution context. Before delving into how we can induce or derive or simulate a null distribution, let's define how we can calculate the p-values from that bootstrap sample. Now, we're starting with the one-tailed bootstrap because we see there's two very similar but slightly different definitions depending on the direction of our hypothesis. For example, in this top spot here where I've put the little curly brackets, if our null hypothesis is that the difference of groups mu x minus mu y is less than or equal to 0, that implies for a one-tailed or one-sided test, our alternative hypothesis is mu x minus mu y is greater than 0. Or in other words, large values of t support the alternative hypothesis. With this idea, our one-sided p-value can be calculated as the probability that t is greater than or equal to t naught, given the null hypothesis is true, which is equal to p sub b, where we just have that subscript indicates from the bootstrap. And we see here for the bootstrap, the nice thing about it is that it's simply counting up the number of times our ti star, or our bootstrap resample statistic, is greater than or equal to t naught from the sample we observed. And we just add those up and we divide by the number of total bootstrapper samples b. Likewise, down below, we can also, if we flip that hypothesis, essentially just flip our directions of our inequalities and once again get our one-sided p-value. Now, it's worth noting, depending on if you look at some different references, some propose adding a value of 1 to both the numerator and the denominator to avoid the possibility of having a p-value of exactly 0. There's no solid agreement about which one is quote-unquote right or wrong, just you'll see both versions out there in the wild. We're also oftentimes interested in estimating a two-tailed bootstrap. So for the sake here, we're going to assume that we have some null distribution, which I'm sketching up here, and we'll say it's centered at 0. We're going to assume that t naught for this illustration is greater than 0, so that's the statistic we observe here, so maybe I'll make a little note right up there at the top. Now, what we're going to do is we're going to try to calculate from this distribution the probability in each tail being as or more extreme than what we observed. So for example, the upper tail in this case is somewhat easy. We see that it would be this top part of the figure that I lightly shaded in. Now, we can also propose the sort of opposite extreme value where we might say, okay, the value of negative t naught over here on the left-hand side, which would be as or more extreme in the other direction of our tail, or in other words, shading that lower region there. Now, the important thing for these is that we account for the fact that it's two-tailed or two-sided. Now, with both of these quantities, we actually have 4 different strategies that have been proposed by different researchers and different sources. Now, I've ordered these from what I consider to be most to least conservative, as well as a strategy based on a one-sided p-value. Now, the first example here is the most conservative, and we would take the upper and lower tail, and whichever probability is larger, we double that one. So essentially for a two-tailed test, we're taking the larger value and we're conservatively assuming the worst case scenario. Now, option 2, on the other hand, allows for asymmetry in the tails. Essentially, we just add the two tails together, so if we had 10% in the top tail and 14% in the bottom tail, we would actually add that to be 24% or 0.24 for our p-value. Now this again allows for asymmetry, so we don't force anything about assuming that the distribution, whether we plot it or look at it or not, is or is not symmetric. Now, a more liberal or likely to find a difference, even if it might not be their approach, would be to take the minimum p-value and multiply that one by 2. So here we see that we just take 2 times whatever the smaller tail range is. Now, options 1 and 2 represent 2 possibilities actually of strategy 4 down here at the bottom, which is actually just based on calculating our one-sided p-value of interest. And essentially this one proposes multiplying the minimum of the one-sided p-value by 2, The idea being here that we see that in this case we have t greater than or equal to t naught and then t less than t naught. So essentially these would sum to 1, but if we doubled the one that has a sum greater than 0.5, our p-value would be erroneously larger than 1, which is not possible. But we can note that by taking the one-tailed or one-sided p-value multiplying by 2, what we're really doing is we're either assuming that that tail is symmetric and has the larger or the smaller p-value available. Again, options 1, 3, and 4 are assuming symmetry of our distribution. In other words, the probability should be equal, or we expect it to be equal in the upper and lower tail, whereas option 2 provides the most flexibility and allows for asymmetry. One interesting point to also raise is this idea of the 99 rule, or in other words, how many bootstraps should I calculate? And again, we've discussed this before in the context of case resampling when estimating the standard error confidence interval, and we really just said bigger is better. And that's still true here. But when estimating a p-value from that null distribution, Boost and Stefanski recommend following the 99 rule. Or in other words, do resampling numbers that end in 9. So for example, if you're doing a simulation study with nested resampling or nested bootstraps, maybe you're doing a smaller number like 19 or 99. Even if we're doing larger numbers, maybe we should do 999 or 9,999. Well, you might wonder, what's this rule of 99, or essentially why should they end in 9? Well, it does connect to some of our statistical theory. Under the null hypothesis H0, we know that p-values are uniformly distributed. In other words, it's just as likely to get a p-value of 0.02 as it is to get one of 0.98 as it is to get one of 0.7. Therefore, under this assumption, if we have B bootstraps, we really have B plus 1 different possibilities. In other words, we could have it be that none of them are meeting the criteria of our calculation, or all B of them could, or anything in between. But essentially, if we had 99 or 100B, we would see that we get two different approaches to estimating this approximate p-value of our probability, assuming the null is true. So for example, we see here below that in our little R output here, we just make a sequence of values from 0 to 1, breaking it out to be either of length 100 if it's 99, because again, B plus 1, or if it's B equal to 100, of length 101. What we see is that for B equals 99, if we're calculating the probability that this equal chance of a p-value being less than or equal to 0.05, well, we have 5 instances. We have 0, 1, 2, 3, and 4, or 5 total. In other words, we actually meet in our desired alpha level of 0.05. However, if we actually fit 100 bootstraps, we actually might overestimate slightly the p-value, because here we see that we'll have an additional 6 value here that is less than or equal to 0.05, suggesting we have 6 out of 101, or 0.059. So essentially, if we want to maintain alpha, long story short, and especially with smaller bootstrap samples, we should follow this 99 rule and try to do resampling that ends in 999, 9999, and so forth. So let's now dig into an actual data example and also talk about how we might derive these null distributions under the setting of two different means. So let's introduce our real-life data example. And this is from the American Statistical Association's Teaching Statistics in the Health Sciences section and their blood storage data set. We're going to explore from the dataset if there's a mean difference in preoperative prostate-specific antigen, or PSA, between tumor stages, which is a binary grouping in the variable, which essentially for our case in our notation, we're going to have group X with 267 or M observations, which has the lower tumor staging, and then the other group will label Y, tumor stage 2B to 3, which only has 34 cases. Now, the data below gives us some summaries and some general distributions of the data. So the first thing we can note is that it appears to be, somewhat right skewed. We see that there's some long tails here, especially for the higher stage or Y group. We can also note that that seems to hold true if we look at the summary statistics, where the means are higher for the red or the higher stage group. And also we don't have equal variances or equal standard deviations here, where we have 4.9 versus 10.9. So this suggests that if we just collected this data and we're trying to, let's say, compare the two means, we might be a little wary to, let's say, just do a two-sample t-test because of the skewed nature of the distribution, the unequal variances, and be uncertain that given our sample sizes, maybe normality may not be met. to address this, we could explore doing a bootstrap approach and potentially calculating a p-value, as we will do in this lecture. Now, we're going to consider 3 different statistics actually, and we're going to just briefly highlight the pros and cons of each one and kind of where they come from. So the first statistic of interest here, D, which we're calling D, will be equal to just the mean of x minus the mean of y. And this is really what I think of as the most similar to what we did previously for Bootstraps in estimating the variability or standard error of a statistic and or its confidence interval. Essentially, we're interested in the mean difference, so we estimate and bootstrap the mean. The challenge here, especially if we're thinking about this in the terms of a p-value and maybe its potential analogs to a t-test, is that this statistic actually doesn't account for any potential differences in the standard errors between groups. So we're just really looking at the means, and we don't account for the fact that there might be potential variability also driving the difference or lack thereof. Also, one challenge or limitation with this is that it doesn't really align with test statistics we traditionally or typically think of when calculating p-values. Those are more of 2 and 3. And in fact, in options 2 and 3, what we're really proposing from Boost and Stefanski is just the t-statistic we calculate to do a 2-sample t-test. But in option 2, we're assuming a pooled or equal variance assumption, which reflects that 2-sample t-test of equal variances, which still doesn't actually account for potential differences in those standard errors between groups, or rather the differences in standard deviations, compared to then option 3, is the most flexible, where we allow there to be unequal variances in our t-statistic. This is the most flexible, accounting for still the standard error of our estimators in that statistic. So moving forward, we're actually going to see and compare results to all 3 of these to see if there's any changes or nuance depending on which one we choose and how the p-values may be affected. Now, as I alluded to earlier, deriving the null distribution can be rather tricky, and we're actually going to just focus on 2 strategies proposed by Boost and Stefanski. In strategy 1, we're actually doing something quite similar to a permutation distribution. We're going to start by pooling all of our data together for x1 through xm and y1 through yn in one pooled data set, and we're going to resample with replacement, though, m cases from this pooled group to assign to group x, and then n cases to assign to group y. Essentially, by pooling everyone together, we're assuming that they have a common null, but also a common or identical variance. So that can be one limitation of this approach, especially as we know in our case, it doesn't look like the standard deviations or variances are equal. Now, if we're trying to specify what type of null hypothesis we're testing here, it's this idea that we're specifically comparing f of t equals g of t, where f and g are the distribution functions representing x and y. Or in other words, what we're really saying is that we think both x and y have the same, let's say, normally distributed data set with the same mean and the same variance. Now, we can actually relax this assumption by looking at strategy 2. Here we will actually focus, and we're calling this the centering strategy. For each group, we're not going to pool them together, but instead we'll subtract from each observation its respective group mean. So we see, for example, our x's become x1 minus x bar, x2 minus x bar, up to xm minus x bar. And likewise, for the y observations, we'll do y1 minus y bar up to yn minus y bar. And we'll resample within each group the respective sample size of m for x and n for y. What this does is that it centers each group mean at 0, so when we're thinking about comparing the means of the 2 groups, there should have no difference, but by not pooling them together overall, it does allow them to maintain equal variances. In other words, if we're trying to formally state this in a null hypothesis, what we're really testing in a more general sense is just the means are equal. Mu x equals mu y, and we're not stating anything about their distribution overall or the variances. Now, as just a general note here, it's just worth noting that for whatever statistic you do choose in a Bootstrap p-value calculation approach, your appropriate null distribution can vary, and you'll need to think through it thoughtfully. Obviously, even just options 1 and 2 here for the mean difference can lead to very potentially different conclusions, or at least different assumptions for what's actually being tested specifically. We can imagine as we get more interesting statistics that we're proposing to look at, like the ratio of cost data or variances or other things, we may need to think about how to appropriately derive a null distribution so we have valid p-values. Let's now take a look at how we can code up this Bootstrap p-value approach in R for all of these different strategies, statistics, and summaries. Now, the first thing to note here is that we're going to do this for b equals 9,999, following that 99 rule. And we're going to set the seed so we can reproduce this either yourself at home or myself in the future to get the same results. And we'll then set or hard code the number of bootstraps for use in our calculations. We see here that we have some data preparation steps to use to separate the data into x and y, as well as the number of observations m and n. We'll then calculate at the very bottom here just the observed test statistics for our data, whether it's D, the pooled t statistic, or the Welch's t statistic, allowing for unequal variance. Once we have all of that set up, we can look at two separate slides here. The first one focusing on strategy 1 of using a pooled null. So here in this strategy at the very top of our slide, we see that we're going to create a new vector combining x and y. We'll then also calculate or generate objects to save our resulting calculations in across all of our iterations or bootstrap samples. We then see here that down in the code, we're going to implement this for loop. And the first thing we're going to do is resample with replacement from the pooled data set of size m and n. So remember, because it's pooled, the same person can actually appear, or the same person's data can appear in both x and y. It can appear multiple times potentially. But once we have that information, we're going to go down here below and just calculate the statistic for this bootstrap resample, where in the first line, we'll just simply take the mean difference of x boot and y boot. And then we'll leverage the fact that the t-test can return and pull out the statistic, whether we assume equal or unequal variances to store for each result in the pooled null case. But here, this is very similar to the two sample bootstraps we've done before, where we have a very, generally speaking, simple or straightforward for loop to implement this process. Now, this slide focuses on our second strategy, which we're calling that centering or centered groups. We see at the top here, the lines of code do something very similar. It initializes our data for the strategy. So we center x and y. So we have x underscore center, y underscore center. So each data set has a mean of 0 if we were to calculate that. We then initialize objects to save our resulting bootstrap or sample statistics in. And then we see below that we're going to have very, very similar code that we had before. Just that in this case, instead of pool, we're going to sample from x center for the x group cases and y center for the y statistic estimates. At the very bottom again, we see that we have just the calculation and storing of each one of our bootstrap iterations. Now the following code provides an example for each of those 4 p-value estimation strategies that we're assuming for a two-sided p-value calculation. And here, just to illustrate it, we're using the pooled data null, noting that this will generalize to all the various combinations we've discussed, and we'll calculate it for the Welch's t-test statistic. Now, just as a kind of reference point here, we can note that the t-naught for the Welch's t statistic in our sample was negative 2.7. So we see here the first thing we're doing in this code is calculating the proportion that are less than or equal to negative 2.7 in that observed tail, and we're also then proposing the counterfactual negative t naught tw to calculate the proportion in the upper tail as well. We can then see that the proportion of results here suggests that the upper tail proportion actually has a much larger proportion of 0.0335 versus the lower tail having a proportion of 0.0004. Now again, for our 4 strategies we discussed, the most conservative strategy 1 will take the larger of those 2 p-values and double it. Strategy 2, on the other hand, will just add them together. Strategy 3 can be thought of as the most liberal of these first 3 strategies because it will just take that smaller one and double it. And in this case, strategy 4 will mimic strategy 3 because it is taking the observed very small p-value and choosing to double it. And we can see that below in our results where the last 2 are both 0.0008. We actually see that by doubling the more conservative max value, we have an insignificant p-value at 0.05, and that by adding them together, we do still have a significant p-value less than 0.05. We can actually summarize the results of our two-sided test bootstrap across all these combinations and make some general conclusions. First of all, in this case with this data, it turns out actually if our alpha threshold is 0.05, the results really are all less than 0.05 and kind of agree, except for the one case of the pooled null for the Welch's t statistic with the most conservative approach. Now again, there's some issues here where the pool null is assuming equal variances already with the pooling of the data set, so there might be some things to consider with that. The second thing to note is that actually the unequal variance t-test that we looked at on the previous slide with p of 0.011 might not be conservative enough. We actually see that in our, what I would argue to be probably the most appropriate case, t sub w of the centered null, both of those p-values, while still significant, are greater than 0.011. Given that the data in our case did not appear to have equal variances in each tumor stage group, I would argue the centered null approach may be more appropriate than the pooled null for the specific Bootstrap implementation. Similarly, it may make more sense to evaluate d or t sub w to avoid making any assumptions about equal variances on our test statistic t sub p. Finally, we may wish to use approach 1 to be more conservative or approach 2 to avoid using symmetry in the tails, which again for the most part in this case didn't lead to large discrepancies except for that pooled null case that we saw for t sub w. So in summary, for Bootstrap p-values, this lecture expanded our use of the Bootstrap from estimating just the sampling distribution of a test statistic for calculating its standard error or confidence interval to calculating p-values from a bootstrapped null distribution. As we saw in the lecture, though, there are many nuanced decisions we have to make along this journey, which is probably part of the reason Bootstrap p-values aren't as popular as, let's say, just interpreting the confidence interval from your Bootstrap distribution of the test statistic. And while there is no one correct value, I would argue that in many cases it's better to select more conservative p-value calculations to avoid type 1 errors or false positives. But again, this does depend on your research setting. Now, these approaches we've described are all general and can be used to estimate p-values for other bootstrapping approaches as well. And we can always interpret the bootstrap confidence intervals I mentioned to evaluate if our null hypothesis value falls within the interval to make a decision if we're willing to forgo the p-value. Well, with that, I hope you've enjoyed this discussion of how we can calculate bootstrapped p-values and some different strategies to do so, and hopefully I'll see you around in the future for some more discussions of different bootstrap topics.